multiplication becomes convolution becomes multiplication. And of course, yeah, the converse, multiplication becomes convolution too. So both ways. So if there is convolution in one domain, in the other domain you have multiplication. So the convolution multiplication property with the DFT implies periodic or circular convolution, which is an important point to remember when filtering. When you filter in the space domain, you apply a mask and filter, and there is no issue. But when you do convolution in the space domain and you want to look at the corresponding effect in the frequency domain, then we have to remember that there is a distinction between periodic and circular convolution versus linear convolution, which is what we are seeing. And I'll show you some examples later. Multiplication of images leads to convolution of their Fourier spectra. Convolution leads to multiplication. Multiplication leads to convolution in the other domain. In time domain signals, it is not common to encounter multiplication. You encounter addition of signals and convolution. But in images, it is possible. What you're seeing here is a multiplication of an illumination pattern of the lamp there. It is transmitted through some sort of, let's call it transparency with these letters, and that is projected. So if I put this, then that is multiplied with the transmittivity of this, which is 0, so you get my shadow. So the image you see, or record, is a product of the illumination function, the light field, with the reflectivity, if I take a picture using a camera, reflectivity of your, whatever the pattern here is, or transmittivity if I'm sending it through film or some transparency. So GXY is FXY times SXY. S is the light source intensity field. Normally we assume SXY, the light, to be uniform, in which case there is no problem. But typically around the edges, around the periphery, there could be some reduction in light intensity, or there could be some other modulation. If that happens, then your image is distorted. Sometimes it is used for advantage by projecting some other pattern to analyze the contours of the body and so on. So there are some benefits to purposefully introducing modulation and multiplying the image with some other pattern, a known pattern. But in some cases, this pattern may be unknown, and that causes non-uniform illumination, and you may want to correct for that, especially in imaging of the retina using cameras, fundus cameras. If SXY is absolutely uniform, its Fourier transform is a delta function. Constant field, Fourier transform is delta, with some value A. And convolution with delta doesn't matter. It doesn't have any effect. So convolution of FUV, the A delta, will have no effect. Otherwise, GUV, the Fourier transform of the image that you have acquired, is the convolution of the Fourier transform of the original unknown image with the source illumination function in the frequency domain. That convolution mixes up the frequency components. And if you want to correct for that, you have to do deconvolution. And for that, there are homomorphic filtering techniques, which I'll show later on. So all of these properties of the Fourier transform have important implications in practical applications, and I'll show them later. First the theory and then some applications or examples. The correlation of two images is expressed in terms of Fmn times G m plus alpha n plus beta. Now the shift is given as plus, and the integration or summation is on m. So there is no reversal. Convolution, you have to reverse one of the signals. But here there is no reversal. So you have one image, you have another, put them together and shift and multiply, integrate for every position. So that tells you what is common between the two. You can do template matching. If I'm searching for some pattern, I take a picture of that pattern and multiply every position where I want to search for that. Where I get a match, that output will be large. You can compare images, two images of the same person or some other picture that you want to compare. What is common between the two? Is there anything common? Maybe there is a target and it's displaced here. So you want to find that. When you take the Fourier transform, you get the Fourier transform of the two images multiplied, but with one conjugated. Similar to convolution, but because there is no reversal, one of them will be conjugated. If you want to normalize the correlation coefficient, then you multiply the two images, integrate, and normalize by the geometric mean of their energy values. There is no shift here. If you want, you can put a shift, m plus alpha, n plus beta, and do it for every shift. Otherwise, if they're registered, the images are registered, you just want to compare for any changes without shifting. Just multiply the two images. It's like take the dot product. It's a dot product of projection of one image onto another, summed over all m and n. This is the energy of F. This is the energy of G. Multiply and square root. That is the geometric mean of the energies of the two functions. Now gamma will be between 0 and 1, or plus and minus 1, depending upon how the changes have been made. Differentiation of an image leads to high-pass filtering. If you take the partial derivative of fxy with respect to x, you get j2 pi u fuv. Some of these you can prove easily. Take the Fourier transform definition, apply the derivative. You will get this j2 pi u out from the exponential. You have done that in 1D. The same is happening in each dimension now. If you do in the y direction, you get j2 pi v. So what is it doing? It is giving you the spectrum of the original image multiplied by this j2 pi v. Take the magnitude, just v, forget the 2 pi. It's increasing linearly. So the gain of this filter is increasing linearly with frequency. So high frequency details get more gain. Low frequency components get lower gain. DC gets zero gain, so DC is removed. So you lose the intensity, the average intensity is lost. Brightness is lost when you take the derivative. Higher frequency components are related to edges, so edges are emphasized. But there could be noise present at higher frequencies, so noise will also be increased by this operation. It is useful in edge detection, as you will see later. With digital images, you just take the difference. Derivatives are approximated by first order differences, fmn minus fm minus 1n. Now, is this horizontal or vertical? It depends upon the array notation or matrix notation, which one you use. So this is where I said one needs to be careful in the interpretation and implementation using array notation or matrix notation. The directions will change, horizontal or vertical. So if it is y or x, it depends upon which way, matrix or array. And sometimes it doesn't matter, but in some cases it will matter. And the other derivative, fmn minus fmn minus 1. The previous pixel along the horizontal or vertical direction. When you take differences, there could be negative values. So the question is, you want to display the result, how do you display negative values? You may take absolute, but then you won't be able to differentiate between an increase of this step or a decrease of that step. Both will come out the same way. So you may want to shift the whole thing. Find the minimum, maximum, and transform linearly to 0 to 255. So there will be an average gray level for 0. Negative values will be dark, positive values will be bright. I'll show some examples. So you need to map the full range of the pixel values, including negative values, to the display range available, typically 0 to 255 using 8-bit display. Magnitude may be displayed if the sign of the results is not important, but typically it will be important. Differentiation results in the removal of the intensity information. The brightness is lost. The values of the spectrum for u equal to 0 or v equal to 0 will be 0 in the result. Like this. The rectangle That's what we had. Differentiation this way, you have that, negative and positive there. And this is the Fourier transform. And differentiation that way, you get this, and this is the Fourier transform. Lines, this is a sinc function, but of two lines. This is also a sinc function. At DC, it is 0. Brightness is gone. If you take the integral of this, it will be 0. Not in the display, but the actual pixel values. Okay? So the myocyte image I showed earlier, I rescaled it, Fourier transform, differentiation, horizontal, vertical. You see some edges here. Here, these edges are emphasized. There, some vertical edges are emphasized. Depends upon the orientation. This is an MR image of the knee. It doesn't matter. In this example, it's just a picture. So when you take the derivatives, you get the edges. And the Fourier transform shows some oriented components because these are like lines at different angles. Note that this is 0 here, and it is 0 there. So taking derivatives is useful in the detection of edges and rapid changes. Small changes will give you small values. You may not care about that, but large changes will relate to large differences or strong edges. When you combine the derivatives and take the second order derivatives, you get the Laplacian. The Laplacian is the partial derivative of second order in x and y added together. And in the Fourier transform, the first derivative gives you j2 pi, second derivative gives you j2 pi square. So you get j square becomes minus 2 pi square, u square plus v square. So now you have gain in the frequency domain applied to the original Fourier transform, quadratically increasing in u and v. So higher frequencies are boosted even more than with the first derivative. And you get stronger output for edges in the image, but also noise will be emphasized even more if there is noise. This is isotropic, meaning it is not sensitive to direction. So we also call it an omnidirectional operator. It is sensitive to edges in all directions, whereas the other gave only vertical or horizontal edges. You implement in this manner, the second derivative is fmn minus fm minus 1 minus the derivative at the other place, fm minus 1n minus fm minus 2n. That turns out to be fmn minus 2fm minus 1n plus fm minus 2n. So it's a 3-point difference. But in image processing, causality is not important. In 1D signal processing, your operations have to be causal. You cannot look ahead in time. But in images, you can, what is ahead and behind? We'll say, okay, if I look this way, it is ahead, that way is behind, and top and bottom. If you're scanning using raster scanning, there is some order of scanning. But otherwise, if you're given the whole image, up, down, left, right, doesn't matter. So you can rearrange this and shift by 1. So applying one shift, you get the result as fm minus 1n minus 2fmn plus fm plus 1n. So weight of negative 2 for the center pixel, plus 1 for the next and next. The same top and bottom. So those are the second order derivatives or the Laplacian. I'm sorry, this is the second order derivative in x and y. You combine them, the Laplacian, you add them, you get this mask, minus 4 times for the center pixel in a 3 by 3 mask, plus 1, plus 1, plus 1, plus 1, top, bottom, left and right. The corner pixels are not used. So this is the filter representation called a mask or a 3 by 3 filter operator, also the point spread function of the Laplacian operator. apply it as a convolution. Shift and multiply and integrate over this. So it's a differentiation operation, second order. But when you add all these coefficients, it is 0. So the brightness is removed. There is no average value of the the average value is 0. So this is known as the Laplacian. So it detects edges in all directions for that rectangle image. But you see there are double edges, positive and negative, when you cross an edge. So you get a double-edged output, which you may or may not like. Positive and negative. If you take the absolute, positive, but it's thicker. The myocyte image, the knee image, some images, some edges. So you see all the edges here in all directions. So the opposite of differentiation is integration. And it should be having the opposite effect. If one is high pass, the other is low pass. Integration is filtering, integration, accumulation, so smoothing. So when you integrate alpha minus infinity to xf alpha y, you're integrating in the x direction only, you get 1 over j2 pi u as the gain factor in the frequency domain. And 1 over j2 pi v if you integrate in the other direction. So these are now decreasing with frequency. Higher the frequency, the lower this weight. So high frequency components are suppressed. And that is low pass filtering. Now, in signal processing, sometimes you may integrate from minus infinity to the current time, usually in theoretical representations. But in practice, there is an origin somewhere, and you integrate from there. In image processing, you don't start from somewhere in the image. You integrate over a small area, not from the origin, wherever that is. So you integrate over a small window or aperture. There is no need to integrate over the whole image. If you integrate over the whole image, you get the average value. That's useless. So you integrate to get gxy as 1 over ab. You are integrating over a window of size a by b, half up and down, centered at the current pixel, fx plus alpha, y plus beta. Alpha and beta are the shifts. Integrate d alpha, d beta. So sometimes I use continuous notation because it relates to certain aspects, like the aperture in an imaging system. Here it is square, but typically it will be a circle aperture. So this is also called a moving average filter, because you are integrating here and then you are moving as you shift, as you change alpha and beta for different x and y, you are integrating. So as you evaluate this function for different x and y, you are shifting over the entire image. So you are averaging over a small window. So that's why it is called a moving average filter. The average is taken over a small window that is moving. Typically, the aperture is a small 3 by 3 window, 3 pixels by 3 pixels, centered at the current pixel being processed. So it turns out to be, in the discrete notation, 1 over 9, alpha, beta going minus 1 to 1, minus 1, 0, 1. Fm plus alpha, n plus beta. What is that? Fmn in the middle, previous row, m minus 1, previous column, n minus 1. The previous row, 3 pixels. The current row, 3 pixels. The next row, 3 pixels. 3 by 3. The weight for all of them is 1 over 9. So you can write it like this as a mask for convolution. So this is a rectangle function. It is a sinc function. So your image is, if you convolve the image with this, the Fourier transform is multiplied with this sinc function. The sinc function, the side lobes keep getting smaller and smaller. So it is a low pass filter, all right, but the gain is not uniformly decaying. It is going up and down and up and down and negative and positive, which is not good. So it's not a good filter. It is commonly used, but it's not a nice low pass filter in the sense that You want filters to have a continuous response in the frequency domain, smooth. But this is up and down, but we use this often. You can also do this in 1D, horizontally and vertically, by using only 3 pixels, either along a row or a column. If you write like this and like that, if you want to write 111 to avoid interruption of the text, you write it as 111 and put a transform. So T is a transform. It's a column vector. So watch for that little T there. It's hard to see the difference, blurred that way and blurred this way. But in the frequency domain, you can see these components are reduced. Those components are reduced. This is in all dimensions, 3 by 3. So this much is retained. And all of those high frequency components have been reduced. The myocyte picture again, I think it's enough. 2 pictures will be enough. This is applying the filter in both directions. I'll skip that. They don't need so many pictures. In the book, I put so many pictures, but not necessary. That's the basic idea. Modulation transfer function is a Fourier transform of the point spread function, as I mentioned earlier. Some authors call it modulating transfer function. In electrical engineering, we call it frequency response. MTF is commonly used in image processing, modulation transfer function. In optics, it is called the optical transfer function, also OTF, in some references. So the Fourier transform of the original image that you're trying to capture is multiplied by the modulation transfer function of your system. And what you get is GUV. You don't get FUV. There's always some distortion. So these are the Fourier transforms of the original image or the scene that you want to capture. G is the image that you got, and H is the point spread function. There are some books, as I said, they call this as the optical transfer function, and its magnitude is called the modulation transfer function. So you have to be a little careful when you switch from engineering books to physics books. There could be some change in terminology. If you want to be more specific, you should say magnitude transfer function if you take the magnitude. But there is some variation in the literature. So the width of the point spread function and the corresponding modulation transfer function are important. In the image domain, if the point spread function is broader and broader and broader, there's more and more blurring. But if the point spread becomes bigger and bigger, broader and broader, the MTF becomes narrower and narrower, more and more low pass. So the width of the point spread function and the MTF have an inverse relationship. The greater the blur, the wider the PSF, and the narrower the MTF, more low pass. More high frequency components are attenuated significantly. Resolution, I mentioned a few definitions of resolution. You can also define that in the frequency domain. Some of us, especially in electrical engineering, we like to work in the frequency domain. It is a point along the frequency axis beyond which the attenuation is substantial, significant. How do you define significant, substantial? You have to set some rule, 10% of the maximum something, and say, that is my resolution. Beyond that, it's too much of loss of frequency components. They're being suppressed too much. You can also take the area under the MTF. If the MTF is big and broad and going to high frequencies with substantial values, there's more area under the curve. If it is flat, it means there is no loss. More area. And if it is narrow, very, very blurry, low-pass system, the area under the curve is very small on the whole axis. So area under the MTF is another measure of the resolution indirectly. Larger the area, the better the system. because it is passing more frequencies with good gain. More high-frequency components are preserved than a system with a small area under the MTF. So here's a practical application of that. I got this from a paper here. And they have compared the MTFs of a digital radiography system. These are old, but the illustration is important and very illustrative in the sense you are comparing the MTFs of a few imaging systems, whatever they are, it doesn't matter. One is a DR, digital radiography system, with an image intensifier television. In those days, they were using a TV camera and then digitizing the TV signal to get a digital image of a radiographic image mounted on a light box. Old technology, and then screen film system, X-ray with X-ray imaging with film plus screen. And FS is focal spot. I mentioned earlier, if the focal spot in the X-ray tube is too large, there is blurring. So they are comparing here. This is image intensifier TV with 0.8 millimeter focal spot and with 0.3 millimeter focal spot, and this is screen film. Obviously, screen film was at that time better than the digital. More area under the curve. This is normalized 1 up to 5 cycles per millimeter. Here, the two of these digital systems are fairly close. There is not much of a difference, but there is a small difference. The larger the focal spot, the more the low pass. The area is reduced a bit. Okay? So all of these, as I said, are important in practice. There is another type of representation of image quality in terms of contrast detail. It's based upon experiments with images of objects, square or circle or something. The threshold object thickness is determined as that related to the lowest contrast image where a radiologist or whosoever is using the image could visually detect the objects with a 50% confidence level. So you make a phantom, a test image. Typically they use foils of gold, could be aluminum or some metal, different thickness and little pieces, squares or whatever you want, and different thickness and different size. If you just want contrast, just the thickness is varied. The thicker the material, the more the attenuation of the X-rays. And if it is very thick, there is more attenuation, so contrast is reduced. If it is very thin, X-rays pass through, you get higher contrast. So as this arrangement is done and you go through that, you ask the viewer, can you see all of these? Or where is it that you cannot see the objects anymore? And you say, okay, that's my resolution. But you cannot just do it once. So you say, do it many times. And then you calculate 50%. 50% of the time, the viewer should be able to detect that object. Then it is passed, otherwise it is not. So you find the cutoff point where the observer cannot see the object anymore. That is the contrast at which detection fails. And you can plot that. Object size, millimeters, threshold object detection, thickness in millimeters. And then for different imaging systems, the image intensifier TV digital radiography system, screen film system. They plotted these curves. So for a given object size, with the screen film, you can detect thinner objects. With the digital system, the object has to be thicker in order to be detected. MTF curves here for screen film, an amorphous selenium detector, and indirect digital mammography. Digital imaging system, but indirect meaning there is an analog system that is scanned. So this was from a company called LORAD. So the indirect digital system is poor compared to screen film, the original analog mammograms that were the standard at that time. The amorphous selenium system is better. Again, you have to look at the area under the curve. Up to 10 cycles per millimeter. So about 0.1 millimeter resolution. So this is how you compare imaging systems using these parameters, modulation transfer function, which is related to point spread and so on. There's an example I'll show you of the MTF of a microcomputer tomography system for high resolution imaging of small lab animals. Nowadays, there are microcomputer tomography systems with a small bore where you can put your hand or put your leg, and you can get high resolution CT images with resolution. At that time, it was 55 line pairs per millimeter. Nowadays, it's perhaps more than that, much better, maybe 100 line pairs per millimeter. But you can't put a whole human body into that, just for the wrist or the fingers and so on, to diagnose arthritis and such issues. The spatial resolution was found to be about 9 micrometers for this system, where this is a French team. This is old, 1996, but this illustrates what I talked earlier about with the edge spread function, line spread function, and so on. They first got the edge spread function. Taking an image of an edge, it's certainly not a step function. There is some blurring. They take the derivative. This is the line spread function. From that, they derive the MTF. Isotropic, so they are showing only this one section for positive frequencies, up to about 80 line per millimeter, it is 0, it's gone. So they did some measurements and said up to 55, it is good. Gain of 0.1 compared to the maximum. So they said that's the limiting resolution, 9 micrometers at that time. So now it'll be much better with new systems. But I like this illustration that all these things we talked about can be put to real use. When there is noise, typically we assume noise to be additive. In 1D signal processing, mostly it is additive. In image processing, sometimes it could be additive, and most of the time additive, sometimes multiplicative also. But let's start with additive. GXY, the image you get, is FXY, the original image, plus eta XY, some noise field. So we are assuming it to be additive and also statistically independent or uncorrelated with the image. That's an assumption made. If you take the mean, mu G is mu F plus mu eta. But mu eta typically is 0. Random noise will have 0 mean if it has positive and negative values. There are some types of noise, like Poisson noise, which only has positive values. Then that doesn't work. So if your noise is having 0 mean, then the mean is preserved. The variance is sigma square G is sigma square F plus sigma square eta. So the sigma square is a measure of the energy, the variability in energy. So that's the mean squared value. So the mean squared values get added up of the noise and the original image. Signal to noise ratio, there are a few different definitions that are commonly used. One takes the ratio of the variances of the original signal and the noise. How do you get the noise? How do you get the original variance? You need to estimate that. And 10 log 10 of it is already squared. If it is not squared, you take 20 log 10. So variance of noise is estimated by computing the sample variance of pixels from background areas or with your camera shutter closed or your cap closed. But the CCD detectors will have some noise. You measure that. No input, no light input. That's an estimate of the noise. Or you may have an image where that's the image and there's nothing here. So you take a few pixels from here, take the variance. That's noise, because nothing is supposed to be here. Variance may also be computed from the PDF or the histogram if you have it. The variance may not always be useful. Sometimes what is more useful is the dynamic range. Variance of the image in particular is not always useful, but you want to know what is the range. So another measure of SNR that is commonly used is Fmax minus Fmin, the dynamic range, normalized by not the variance but the standard deviation, just to maintain the dimension, and 20 log 10 because they're not squared. Typically, in the days we were doing our research, this was expected to be of the order of 60 to 70 dB. 40 dB, most researchers were happy. But 60, 70 dB was considered to be very good signal-to-noise ratio in image display systems. Again, nowadays that's much better. These numbers may not be relevant at this time. What is also important in display is what is the frame repetition rate in your display so you get a steady image, and is it interlaced or not? Are you displaying all the data or are you displaying only alternate lines like in old TV? But perhaps you would not encounter interlaced display now. They will all be non-interlaced perhaps. Contrast to noise ratio is another measure where you see something similar to background, foreground minus background divided by background. But now it is a mean of the foreground minus mean of the background, like what we had F minus B earlier, but the denominator is sigma B. Sigma is standard deviation of the background. And that could be computed in a background around the object or somewhere else in the image. So it's an estimation of the noise standard deviation. So then that's a measure of contrast to noise ratio, not simultaneous contrast. When you compare images, you could take a few different measures. Mean squared error, FMN minus GMN square, averaged over the entire image. Mean squared. It's not an error, it's a difference. Normalize that by dividing by the energy of the original, F. So the same thing, divided by that, the Mn cancels out. Normalized error, you take the magnitude instead of square. Laplacian says, well, the actual values in the image could be shifted. You're comparing one image with another. Maybe it's the same scene, but I took two pictures with different light levels. The mean squared error will be very large because the intensity values are very different, but the scene is the same. So Laplacian says, don't compare the images, but take their Laplacians. Remove the intensity out and take the relevant edge information, which is important in understanding the scene. So FL is the Laplacian of F, GL is Laplacian of G, normalize with that. That's called the Laplacian mean squared error, which will account for variations in brightness or intensity or exposure. And then there is a measure known as perceptual MSE. In image processing and analysis of imaging systems, some of these errors are mathematical concepts or statistical concepts. But what matters in perception is how our human visual system perceives the details, or how the radiologist or the user perceives. So you have to bring in the characteristics of the human visual system, which acts like a filter. It's a high-pass filter. It's a band-pass filter. Not exactly high-pass. There is a high-pass component in a band-pass filter. Some model it as Gabor filters. So you use that filter instead of the Laplacian, and then compare the images. So PMSE is defined in a manner similar to the Laplacian MSE, but images replaced with a log of the image convolved with a PSF representing the visual system of either the user or the general population. Now these are comparing images before and after, assuming you have the original and then something else that was somehow modified. But you don't always have that. You just have perhaps what you acquired from an imaging system. You don't know what the original is or was. There's no such original thing. You just have the distorted image or the acquired image. Then you need other types of measures. All of these measures need a reference. You need reference-free measures of whatever it is, contrast, high frequency, and so on. So there are some such measures. So I'll now go through one of the applications we worked on based on what is called acutance. Acutance is an interesting concept related to sharpness, edge sharpness, similar to the edge spread function we saw earlier. One of the definitions is the derivative of that edge spread function squared, a to b, where the edge is between a and b, and divided by fb minus fa, the value of that, so you normalize it. So this is acutance. Ideal edge, the blurred edge, more the blurring, the lower the derivative. And integrate between the limits of the blurred edge and normalize by these values, fb minus fa. So that has been called acutance. It is based on the image domain using an edge function, edge image. So many experiments were conducted in order to compare films in the olden days, in the 60s. There were many types of films for X-ray imaging, for mammography, and so on. You want to compare them. How do you do that? Create an edge object, take a picture, take the edge spread function, which is that, and get the acutance value. It was also done with photographic films. And prints were made, or some display was made, of the blurred edge images. They were given to a number of observers. They were asked to rank the blurriness or sharpness. And then this was correlated with sharpness as judged by human observers, and it was shown to have good correlation. So it relates well to how human observers will compare or analyze sharpness and rank across multiple images. So they use this to analyze and rank the quality of films for photography and other types of applications. And then there are a number of other measures also called acutance. They use the same name. I wrote a review on this many years ago.
The earlier process, the reverse also can be used like to test the eyesight or something like that.
Could be. Like what you perceive, but you have to explain what you are perceiving, right? So this is to correlate a mathematically derived and computed measure with what a number of human observers have seen. It is assumed they're all standard observers, but some may have some deficiency or some difficulty in observing details. That's why you take a number of observers and average. So you may rank it as 1, 2, 3, 4, 5, and she may rank it as 1, 3, 5, 6. The ranking will be different, so you average. We noted that the area under the MTF curve is important. So the MTF has been used, and the MTF of an entire chain of systems along your imaging process needs to be taken into account. First, you have your X-ray system, and you take a picture on a film, but before the film there is a screen, and there could be a grid, and then you take that and perhaps you digitize it, and then you display it on a monitor, and then you are sitting and watching, so your system is the final one. So there are multiple systems in this chain of image acquisition and display and analysis. So H1 UV, H2 UV, when you have a number of linear systems in series or cascade, the net or total MTF is the product of all the individual MTFs. The image final output is the convolution of the input image with the convolution of all of these point spread functions, because it's going in cascade. So you take that product and take the area under that curve. There are different ways of normalization. The basic idea is a system with large gain at high frequencies will give you a sharp output image. That means large area under the normalized MTF. But MTF area-based measures represent the combined effect of all the systems between the image source and the viewer. It doesn't depend upon the image. So it depends on the system and the viewer and has nothing to do with the actual image, which may be good or bad depending on what you want to do. So if you use radial frequency, nu is square root of u square plus v square, then a measure of acutance was defined as hs nu minus he nu integrated 0 to nu max in the frequency domain. So hs is the MTF of the complete system. He is the threshold of the eye, MTF threshold. Nu is the radial frequency of at the eye of the observer. So that depends on the distance between the display and that's the angle subtended. Nu max is given by this condition. Hs nu max must be equal to He nu max. So that was another measure. And then somebody else said, well, don't take a difference, take a ratio. I can go 0 to infinity or 0 to some limit in frequency. And another researcher said, well, we need to normalize and get numbers like in marking exams up to 100. So scaling factors. So they said 100 plus 66 log 10 product of the two MTFs divided by the integral of the I MTF ratio. This is just a normalization factor, so 100 is excellent. And 70 is just passable. Not 35%, not 50%, but 70%. That used to be first class with distinction for me. Nowadays, all of you get 99.9, I suppose. For us, 70% was top. The exams were tough. That's what we put the blame on. That's the excuse. But really, 70% was first class with distinction. Is that so now? What is it, 90?
Distinction only like same. Yes.
70. But you're all way above that.
Yes.
Good. Oh, yes. You see, he says yes, and you were nodding your head. Okay. There was another one who said, take the ratio and square root d nu divided by nu, inverse weighting with frequency. You don't have to remember all this, but just know that there are different ways of comparing the MTFs. Difference is one, ratio is another. And integrate and some normalization. Barton has a nice book on just acutance, a whole book. It's interesting. We wanted to extend this definition of acutance to a specific image, to a specific object in an image, in particular tumors. Benign masses in X-ray images have a sharp boundary. The inside is dense, outside is less dense, and the boundary is sharp. So if you take a derivative across the boundary, the value of the derivative is high. But we have to take the derivative in a different way, as I will show you. Whereas malignant tumors are blurry. The edges are blurry, and because the cancer is expanding and infiltrating surrounding tissues, there is no sharp edge in the case of malignant tumors. Now, such things we gain by interacting with radiologists and chatting with them, and they would come to our labs, I would go there. To go away from this topic a little bit, it is very important in this kind of work to collaborate. There is only so much we can do sitting in our own labs in front of our computers. These ideas that I'm talking about were given to us by radiologists. They know what kind of images there are and what are the differences between type A, type B, benign, malignant, this, that. And in my opinion, in my work, I felt our task is to encode that, to quantify it, to capture that and write algorithms, develop algorithms to measure that in a quantitative way so we can do objective analysis. The radiologists will say this is blurrier, this is sharper, but put a number on it. for us. I call that collaborative or collective intelligence. As I said, I don't like the term artificial intelligence. Everything is AI nowadays. This is not AI, this is CI, I'll call it. Collaborative, the collaboration is very important. I wouldn't have been able to do this myself. The radiologist, I would assume, would not do that by himself or herself, but together we do something that is useful. That collaboration is important, and credit should be given where it is due. To call this artificial is, I think, demeaning and taking away the contribution of others, not only radiologists, but medical scientists and others. But anyway, the world is going in some way with Trump and Musk and others. So we said we want to get a measure of the sharpness of the edge of objects such as tumors. So instead of using the traditional difference, as we call it, derivative or first difference, Fn minus Fn minus 1 in a single row, we said you jump across the edge. What is inside the object and what is outside, at multiple scales or multiple distances. So if this is the boundary, we said draw a normal at every pixel. Normal is perpendicular to the tangent at that point, the normal. This is the edge point, we don't use it. 1 pixel distance inside and outside, take that pair. What is the difference? If the inside is brighter than the outside, that's a large value. And then do that for different distances, maybe 2, 3 distances. But we're not taking differences like this and this and this and that. And do that at every pixel all the way around. So there is averaging for each normal, and then there is averaging across the whole object. So that is Fn minus Bn, foreground minus background. And the distance between them for n is 2n, 2 pixels, one inside, one outside. And n going 1 to n, some number. That is one gradient at one normal. And then average that over the entire image by averaging over all of these normals. So if there are capital K of those normals, then that is the root mean square value of that. So we call this acutance, not knowing all the history. When we sent it for publication, I got very critical reviews. You forgot all of this. There's so much history behind acutance. So then we went back and reviewed all the literature and put this in the context of all of that. And then it was published. So acutance we showed by conducting subjective analysis, showing images to a number of observers, and computing the acutance value and correlating with subjectively ranked sharpness. So we took a test image, blurred it once, twice, 3 times, 4 times, blurrier and blurrier, added noise, and then we showed that it is reduced by blurring, increased by sharpening, not affected significantly by noise because of averaging of the derivatives, and correlates well with sharpness as judged by human observers. We also applied this to analyze breast tumors in mammograms. I'll show that later on. Okay, that finishes chapter 2. I skipped some parts that are not very important. You could read them later on. We will switch to chapter 3 now on filtering, and that includes, again, some background on linear shift invariant systems, convolution, some numerical examples. I'll go through them quickly because many of you already know that. But are there any questions right now before we switch to the next chapter?
Rather than remark, you said I started feeling that is true,
It is.
not giving credit to the radiologist or medical scientist, but in artificial intelligence neural networks, we need the knowledge of that. Finally, we don't even credit to the artificial intelligence, it takes over
Yeah. Excuse me. What has been shown is that AI-driven, deep learning-driven systems have catastrophic failure. They're trained with a certain data set, let's say in Europe, with European images, or patients or whatever, and then come to India and put Indian images, they collapse. Because they're trained only with that. Whereas if you extract measures that you have designed specifically, what one of my colleagues has called handcrafted features, like you do a matka or something with a wheel, and it is specifically designed. But it incorporates the knowledge of the radiologist and our knowledge as electrical and computer engineers, and it is expected that it'll work across multiple regions, multiple types of images. The same thing applies to tumors anywhere in the brain or wherever it is. The same thing happens. Benign versus malignant. I've heard from other researchers when I presented this, they say, oh, that's breast imaging, yeah, but it's similar in the brain. And true, that's a basic biological variation between benign and malignant. Whereas if you simply stuff 1 million images, it catches something. I haven't done research in this area, so it's uninformed and biased opinion. But I have read reports where it says some of these systems do fail in a disastrous manner when new samples are presented because they haven't been trained with such. But when we did our research, it was hard to get 10 samples. Now in 30, 40 years, things have changed and there are millions of images available to you. There were no public databases at that time. We had to go and get the films and digitize them, scan them in our lab. My students spent a lot of time doing that kind of work. Now you just go somewhere and download 1 million images. So things have improved and changed, yes, but I think it is important to recognize where this information comes from and give due credit there. There are some computer scientists, I won't name any, who have claimed, well, computers will replace radiologists. There won't be radiologists anymore. And it is true, they have said that, very influential computer scientists have said that, AI specialists. And my colleagues in Brazil who are radiologists have told me that led to a drop in residents coming to radiology. So that is irresponsible to say that and cause such a shift in the preference of students. The students should know better, but they will trust such information coming from somebody who is highly placed. And so, radiology won't be there anymore, so I won't go there. And that's not correct. Okay, now we go to removal of artifacts or filtering. What are artifacts? There could be noise, there could be some kind of a pattern that you're not interested in. So basically any image pattern or signal other than what is of interest could be termed as interference, artifact, or noise. Usually we assume when you say noise that it's random with zero mean and uniform distribution, but not necessarily so always. Anything that you don't want, like that, somebody scribbled there, that's noise. So that's a general opinion, or not opinion, view of noise. But there are different types of artifacts. So when you design filters, you need to know what kind of artifact you have and how to remove that. Random noise is present always. Interference from a random process such as thermal noise in electronic devices, CCDs, and counting of photons, X-ray photons or gamma ray photons. The emission process is random, the counting process is random. So everything is random. And you characterize random processes by their PDFs. So let's call that noise is represented as eta, p eta of eta. So this notation, the subscript is important because that is what the original process is. The argument could change when you integrate and apply various processing steps. So the noise process is simply a bunch of values being thrown out by something, some disturbance in the air, random variations in temperature. You have a number of CCD elements, and each one has some dark current and some noise. Where are you putting those values is the question. If you put them in a time function, in a time series, it's eta of t. If you put them as a function of space, eta x, eta xy, xyz. So those individual values are coming from some random process. If you arrange them in a pictorial format, you have a picture. Otherwise, it could be a time function. So it could also be eta xyz time, 4D. 3D function as a 3D data as a function of time. So regardless of how those values are arranged in your signal or image, the statistics are defined based on the PDF. So mu, the expectation value, is integral of eta p eta. E is the expectation operator. That, whatever that is, multiply with the PDF and integrate. Second moment, mean squared value, eta square. Eta square times the PDF. Variance, eta minus mu square, PDF, integrate. The pictures taken. So even those are random. They're not exactly random, they have structure, but they have variations. So in general, you can say everything is random and treat them as random observations of a random process. Each one is a realization or observation or a sample of that process. So this allows statistical characterization. So a collection of images of the same organ, system, or type, and population limitations, age limitations. You don't want to mix pediatric cases with adult cases. You don't want to mix images of female subjects with male subjects, or Indian with European, and so on. So you have to have separate databases because of variations in the body or in ethnicity and place of living. So collection of images of the same organ, same type, same imaging modality, same settings, everything being the same, then you can characterize them statistically. Take the average PDF, average histogram, then it's a PDF. And then you can characterize them in terms of their statistics. If you mix various types of images, CT with MR and brain and liver, that doesn't help. So statistical averages representing populations of images of a certain type are useful in designing filters. Which filter is most suitable for that kind of image? Data compression techniques, pattern classification procedures that are optimal for that specific type of images. But one should recognize that in medical imaging, we are not interested in the average. Not we, but the radiologist or the physician, the cardiologist is not interested in the average, but what is the difference between the average and this patient? That is where diagnosis comes in. So deviation from the normal is what is important. But that's what they do. So when an image is observed in the presence of random noise, we assume this model, additive noise. And each one has its own PDF, PF, P eta, PG. We assume they are statistically independent processes so that the joint PDF is the product of the individual PDFs. The expectation of G in this case is additive. The means are additive. Mu G is mu F plus mu eta. That happens if due to linearity. But with statistical independence, you also get this relationship. The variance of G is the variance of F plus variance of eta. The powers get added. Now, there are different ways of taking averages. One is with the PDF, if you know the PDF. But if you don't have the PDF or don't know, or you want to do something else, there is the possibility of ensemble averages. An ensemble is a collection of images of a certain type, or the same image being acquired repeatedly for the given situation. So you have a number of sample observations, F1, F2, F3, and so on, of the same I take a picture here, I stand here and take click, 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 and I take many pictures. What is the variation? Assume nobody is moving. The variation could be some noise here or CCD, noise in my detectors. So there'll be some variation. Then I can do ensemble averaging of the images. The whole string of images can be averaged, assuming there is no motion, no registration issue. So you have a stack of images, and the ensemble average is taken using pixels that are registered for each pixel through the ensemble. You can also take spatial averages in one image. If you only have one image, you average like that. But if in an ensemble average, you go through multiple images to get mu of x1, y1 for x1, y1 one location, and do it for each pixel. So mu f x1, y1 is 1 over m, k going 1 to m, f k x1, y1. There are capital M number of observations. For each pixel, you average across those. And divide by m for normalization. Limit m tends to infinity means you need to have a large number of images. Nobody will acquire an infinite number of images, but a large number, 10, 20, whatever. That helps in reducing noise. The autocorrelation function is defined as phi f x1, x1 plus alpha, y1, y1 plus beta, some shift of the given image, fx1, y1, and the same image with x1 plus alpha, y1 plus beta, shift of alpha, beta. Multiply them, take the expectation. I earlier defined a correlation function where you just took the dot product between the original and the shifted version. Now this is in terms of statistics, expectation. That means you have to multiply that with the PDF and integrate. But you estimate in this manner. You say, okay, you have capital M of the images. I don't have a PDF, but I have a number of observations. So over a number of images, Fk, k going 1 to m, and Fk with the shift. And divide by m, large M. If the process is stationary, the autocorrelation function depends only upon the shift parameters, phi f, alpha, beta. So this x1, y1 will go away. That requires stationarity. Then autocorrelation is a function of the shift only, and the Fourier transform of that is not dependent upon the spatial position x1, y1.
So the sample estimate is, we assume that the sample estimate is works in real time, right? That's what we assume.
The value of the noise is reduced. So we call that f bar, and you could call that a prototype or simply a filtered image. But it is filtering through a population of images. So those are ensemble averages, averaging a collection of images. Before that, we said we can take statistical averages using the PDF. If you don't have the PDF, go for ensemble averages. And there are situations where you don't have an ensemble, you only have one image. Take it or leave it. And then you can only work with that one image. Then you go for spatial averages or temporal averages if it is a time domain signal. So when you have a sample observation of a process as a function of time, you may compute time averages or temporal statistics. Mu of k, fkt, now it's a function of t. And that is an observation k. And you make multiple observations, but the integration is on time. The averaging is on time, and 1 over t is normalization over a large time window. Autocorrelation function is this, fkt plus tau. Tau is a shift. Integrate over a window and make that window as large as feasible. So given an observation, fkxy, we may compute spatial averages or spatial statistics. Instead of time, now space. So mu fk is integral of fkxy dx dy, now on space, averaged by the area of the image A. But this is one value for the whole image. The average, mean value, mean intensity, mean density, whatever, one value. Not very useful. It's not a picture anymore. The autocorrelation function is given by alpha, beta, k, where you have kth observation. There are multiple observations of the kth image fkxy and fk with the shift. Dx, dy integrate over space. You may normalize this with phi f00, which is the energy of the image. If you want that to be normalized, then it will be maximum of 1. The sample index k is irrelevant if you only have one image, one observation. Then you can only do spatial averaging on that image. So when you have a TV image or an image as a function of time, and it need not be like multiple frames over seconds, but it could be images of the same patient over a few months or some time. Then you have a series of images, and there is a time factor there as to when the image was taken. So then you have fxyt or fxyzt if they are CT or 3D images. Then you can do all these operations in all the space coordinates and the time coordinate. If you compute the statistics using one frame, it is called intra-frame. If you compute statistics between frames, it is called interframe. So interframe and intra-frame over a 3D data set. So this could be multiple frames of a TV signal or multiple images of a patient over time. And if you take averages over one image, you call that spatial or intra-frame. If you go across the collection, previously we called the same thing as ensemble averages. Now here the ensemble has a time index, so you call it temporal or interframe statistics. So there are many possibilities of getting statistical measures from medical images in 1D, 2D, 3D, 4D time, space, with PDFs, ensemble, and so on. So one needs to recognize which method is suitable or which has been used in gathering this information.
The sequence is not the relation of the sequence that you have shown the frames like this. These are not the relation of any of the.
What's that?
They are not the relation of some random.
No. Here, they are not. Here they are not random. No, this is my image taken today, tomorrow, and so on, or my image taken as a video. So it is an image that is of a certain type and of a particular patient if it is a patient's image over time, or video. There is no randomness here except the noise. There could be noise there. Yeah, even the other case, the ensemble, they're not random. The ensemble is a picture of a scene. My picture taken many times because your CCD camera or whatever camera you're using has noise. If you're using a thermal camera and night vision, then you don't have much light. So there is a lot of noise. So if you take my picture and it's very noisy, grainy, you take multiple shots asking me to be steady, and then average, you get a better image. So the randomness is there in the noise, but not in the picture. Is that what you said? Yeah, okay. So the mean is not important, it's the average brightness, and you don't throw it out, you need it for display. In signal processing, 1D signal processing, often we remove the mean. In speech processing, there is no mean is 0. Mean average value doesn't mean anything in speech. There is no variation, right? But ECG, there could be an average value. Heart sounds, no. EMG, no. Where is mean important? Not many places. But images, the mean is important because that's the average brightness. The autocorrelation function is important in the characterization of random processes, given that the Fourier transform of the autocorrelation is the power spectral density. you get the past spectral density, which is useful in analyzing the frequency content and designing appropriate filters for that class of image. These statistical functions are useful in the analysis of the behavior of random processes, in modeling random processes and also populations of images, spectrum analysis, filter design, data compression, data communication systems, and so on. You need to know these statistics in order to design optimal filters and procedures. If you just want to do something ad hoc, fine. But if you want to do something optimal, then the optimization procedure will require some of these statistics, especially the autocorrelation and MTF. A few examples of 3:30, right? I'm checking. You're okay for 5 more minutes? Anybody sleeping? No. A few examples of PDFs. By looking at the distribution, you should be able to judge what kind of a function it is. Gaussian is this. You have mean and the variance, exponential with the normalization factor. It is completely specified by the mean and variance, only 2 parameters. Looks like that. Everybody knows Gaussians. Different, same mean but different variance and different mean. When you have 2 jointly normal random processes, then the normal bivariate normal PDF is given by this Gaussian with this correlation factor. This is one Gaussian, this is another Gaussian, and the normalization factor includes the variances of the Gaussians and this 1 minus gamma square. The gamma comes here as a weighting factor and here. And gamma is the correlation coefficient given by expectation of x minus mu, y minus mu y, divided by sigma x, sigma y. And if they are uncorrelated, gamma is equal to 0, and then that goes away, that goes away, that goes away. You get a product of 2 Gaussians. So the bivariate normal PDF reduces to a product of 2 univariate Gaussians, and they are statistically independent then. There is a central limit theorem that is important related to the occurrence of Gaussian PDFs and the assumption of Gaussian PDFs. It is common to assume when you don't have adequate information, well, we'll take it to be Gaussian. Why is it important? Because the PDF of a random process, that is the sum of several statistically independent random processes, is equal to the convolution of all their individual PDFs. This is from, if you have seen the book by Papoulis, Random Variables and Stochastic Processes. That's where we studied. When a large number of functions are cascaded and convolved, then all these convolutions will lead to something that is smooth like a Gaussian. If you take a rectangle function and convolve with another rectangle function, you get a triangle. Convolve again with another rectangle, you get a smooth triangle. Convolve with the same rectangle function convolved 3-4 times will lead to a smooth result that looks like a Gaussian. All of these are positive valued functions, so there is only smoothing, no differentiation anywhere. So regardless of the forms of the individual functions, they tend towards a Gaussian. So that's why it is assumed commonly that the noise has that shape. But sometimes we do have uniform functions. Uniform, all equal, all probabilities are equal, all values occur with equal probability. The mean is a plus b over 2, where a and b are the limits of the rectangle, and sigma square is b minus a square over 12, just a rectangle. The Poisson noise is important in imaging, medical imaging, especially in photon counting, single photon emission computed tomography, gamma camera imaging. The counting of discrete random events, such as the number of photons emitted by a source or detected. There could be a number of photons coming, but your detector will not catch all of them. They will catch some. And there is a randomness in the emission process and the detection process. And the discrete nature of photons and the statistical randomness in their emission and detection contribute to uncertainty. You can call them quantum noise, photon noise, Mortal, Poisson noise, and shot noise. depending upon the source and the type of system you're using. One of the formulations of the Poisson PDF, there are at least two. I'll show one here. pk is exponential minus mu to the power of k over k factorial. Mu is the mean, average number of photons counted in the specified interval of time over many trials. pk is the probability of occurrence of k, and the variance of the Poisson process is equal to its mean. But the Poisson PDF tends towards a Gaussian for a large mean, but it is one-sided. So the Poisson PDF ends here, it's not for negative values. But as you increase the mean, it looks like a Gaussian. It becomes close to a Gaussian. This is for mu equal to 4, that is mu equal to 20. The Laplacian is encountered when you take derivatives and differences. And the Laplacian distribution is defined in terms of a mean and standard deviation. And this exponential function, it's an exponentially decaying two-sided function. You encounter them also in linear prediction and prediction error. Looks like that. Laplacian distribution, 0 is in the middle. Sigma square equal to 1 and 4. The Rayleigh distribution is encountered in some types of imaging, especially with ultrasound and a few other types of imaging. Let's not worry about the form. I'll show you the graph of that. It looks like that, which is not symmetric, and it is one-sided. So we'll stop here and take a break. If I'm going too fast, let me know. These are just some basic things I'm reviewing quickly. When there are more important things, I'll go a little slower. But if something is not clear, please stop and ask questions. So let's take a break, 30 minutes.
Yeah, we'll have a tea break now. We'll come back at 4 o'clock.
The second type of artifact is structured noise. So noise is not necessarily random, or you can call it structured artifact. There could be some patterns that appear, such as the X-ray grid artifact. If you go through the first chapter, you will see that in obtaining X-ray images, in between the patient and the detector, there is a grid made of metal strips with some insulation in between. And the grid pattern is there to minimize the passage of scattered radiation. Scattered radiation will hit the grids and will be absorbed there and not hit the detector. But the grid has to move, otherwise it will cast a shadow which will be parallel lines. So the grid is oscillated or translated during the period of exposure. But if there is a problem in that process of movement of the grid, if it starts late or ends soon, or if it doesn't move at all, then you get the X-ray grid artifact. You may use other grids and frames for image registration. I want to take your picture and then I want to register it with some coordinates, or have relative coordinate system within the image with reference to my markers. Labels indicating patient position left, right, and this and that. Craniocaudal view in mammogram, CC, MLO, left, right, and so on. They're supposed to be away from the patient, away from the part of the body being imaged, but sometimes they get too close. And in the projected image, they may fuse or they may connect. They may not connect in the actual situation of the patient and the labels being placed, but in the image, due to the angle of projection, they may touch. Surgical implants such as staples, pins, and screws, if the patient has had some procedure to fix bones, then they're there. You can't do anything about it, they'll be there in the image. Power line interference is common in biomedical signals, ECG, and so on, but in images you don't encounter such noise. I have not seen that. There is not a straightforward way for power signal to interfere with your image signal. But maybe there are some situations where that happens. And then there is physiological interference. What I would like to call physiological interference is some artifact caused by physiological events within the body over which the patient doesn't have control, such as effect of breathing. We do have control on breathing. If it is an adult patient in good condition, you can ask, take a deep breath and hold until I take a picture. But with an infant, it's not possible. With an adult who is not in a good health situation, that is not possible either. Effect of breathing, peristalsis, movement of material through the gastrointestinal system, effect of cardiovascular activity on various types of images, CT, MR, effect of pulsatile movement of arteries and digital subtraction angiography. When you want to take picture, an image of the blood vessels in the brain, then with the digital subtraction angiography, you take, I'll show you that later on, a reference image and then the live image and subtract. But then the blood vessels will be moving due to pulsatile movement of the blood, and that causes artifacts. So these are physiological, they're not random, they're not structured in the sense there is no geometric fixed structure. There is a structure for the patient, for each subject, depending upon the imaging situation, but you cannot model that. So anatomical details such as the ribs in chest X-ray images and the skull in brain imaging and the pectoral muscle in mammograms, they are not of interest. You want to analyze something else, but they are there. So you may want to remove them using image processing segmentation operations. They're not noise, they're normal, but you're not interested in them. You want something else. So those are also parts of the image in which you do not have an interest, and hence you may say it is an artifact. But you can't escape. There could be geometric distortion, miscalibration, nonlinear response of detectors, sampling and quantization we saw. All of these affect the quality of the images. And then a few more. Punctate or short noise due to dust on screen film or on the examination table. There could be some dust. Or the patient may have some cosmetic powder or something, and those are high density specks. Scratches on film, if you scan film and if there is a scratch, but again, we don't do that anymore. Short noise due to inactive elements in a detector array. This happens in your camera, but it is automatically corrected in your camera, so you won't see it. But in medical imaging devices, if you take that CCD, which is not programmed to correct for this, then you may see a few dead spots. Salt and pepper noise due to impulsive noise. Salt is bright and pepper is black, inactive element, or one that is saturated and left there. Film grain noise due to scanning films with high resolution. You may get patterns of the grain, the silver halide grain crystals, on top of the image details. So that is film grain noise. Punctate noise in chest X-ray or mammograms caused by cosmetic powder or deodorants that may appear to be calcifications. You don't want to mislead diagnosis by these. So the instructions before such imaging procedures tell the patient, do this and remove this and don't use this and so on. But sometimes they do happen. Superimposed images of clothing accessories such as pins, hooks, usually they don't happen, but they do happen in practice. There are cases of people walking into an MR scanner with metallic implements, with metallic objects, and that's extremely dangerous because they could fly and hit somebody in between or get ripped out of the body too. There are scanners to prevent this, but they still happen. To characterize artifact, we have a couple of methods and techniques. You characterize them as stationary or non-stationary to begin with. Random processes may be characterized in terms of all of these statistics we saw, temporal, spatial, ensemble. A process is said to be stationary in the strict sense or strongly stationary if all of its statistics are not affected by a shift in the origin or time or space. So if you take a bunch of samples here or there, if the statistics are the same, all statistics, all moments. In practical applications, only the first and second order averages like mean and standard deviation or variance are used. And then it is said to be, if those are not changing with a shift in time or space, then the process is called weakly stationary or stationary in the wide sense. If the mean is constant and the autocorrelation depends only upon the difference or shift in time or space. So mu f x1 y1 is simply mu f. It does not depend on x and y. And phi x x1 plus alpha and all that is only phi alpha beta. So there is no x and y coordinates in these. So the autocorrelation function is a function of the shift parameters alpha beta only, and the path spectral density does not vary with space. So I can characterize the entire image with one power spectral density. But that's not true. In the case of a chest X-ray image, we have ribs here, we have the heart here, and we have other parts where they are smooth, and so the characteristics are different from one portion to another. So to assume one spectrum for the entire image is in the average sense, but it doesn't apply to various parts individually, even in one image, such as a chest X-ray image. So these characteristics are in general spatially varying. A stationary process is said to be ergodic if the temporal statistics computed are independent of the sample observed. I take one signal here, another signal there, another signal at some other time, and if the statistics are the same, then you say temporal statistics from each one. Then you assume the process is said to be ergodic, and then you can use the time averages instead of the ensemble averages. Collecting an ensemble of signals takes time, and there could be some expense. And there are issues with patient movement and so on. So if you can do temporal averages with one signal, it's simpler. For that, you have to make the assumption of ergodicity. In the case of a signal where statistics vary with time and space, it is said to be non-stationary. The statistics of most images vary over space. Only a flat image like this, there is no variation. But even here, these are flat areas, there is something here, and the shape changes, the color changes. So the characteristics change over space. If there is no change, then perhaps there is not much information in the image. It is that variability that gives you the pictorial information. So biomedical systems are dynamic and produce non-stationary signals and images. In the case of heart sounds, you have the first sound, the lub-dub, the first heart sound, second heart sound. There could be murmurs in between, some whooshing, swishing sounds in between, with blood going through some constricted space. Then there is high frequency noise. Low frequency first heart sound, high frequency noise, a little medium frequency second heart sound, maybe low frequency diastolic murmur. So the spectral characteristics change within one cardiac cycle over every 20, 30 milliseconds, the spectrum changes. The same in images, things change. So most of the images we see are non-stationary because the systems generating them are dynamic. They are varying with time. A physical or physiological system has some limitations though. The heart rate can only be so much, maybe up to 250 or so. So if you take smaller divisions of time, you can assume the signal is stationary within that small interval. Or you have a big image, you know this part there is nothing, and this part there is something else there. So you can break into parts and say each of these parts is stationary. So this facilitates the breaking of a signal into segments of short duration. And then you assume each of those to be stationary. You call it quasi-stationary, almost stationary. There is variation overall, but within small sections, it is stationary. This is commonly done in speech signal processing using what is called short-time signal processing. You don't take an entire speech of several minutes and analyze in one shot. That's not possible. You take short pieces, short-time analysis. Within those short windows, you assume the signal has the same spectrum, same autocorrelation. It is stationary. So that is then the notion of quasi-stationary processes. So we have this idea of short-time analysis, or in the case of images, block-wise or sectioned processing. I process this and this and this separately. For each block, we assume the image to be block-wise stationary instead of calling it short-time processing. So section, block by block, moving average, moving window processing techniques may be used. So you don't process the whole thing in one shot, but little windows, and the window is moved around. There is another special case in biomedical signals known as cyclostationarity. Stationary, yes, but not within one cycle, but from one cycle to another cycle, the same part, the same phase of the cycle will have similar characteristics. The first heart sound from this heartbeat to the next heartbeat to the next will almost be the same. There will be the effect of respiration. As my lungs expand, my chest expands, the transmittivity between the heart and the exterior microphone you put there, the intervening medium will change. So there will be some variation. But if you go within the heart, quite likely, if you put a microphone within the heart, you can do that. Not you, but trained people can do that. Then it is possible that those successive heart sounds, first heart sound is the same, second is the same. The murmur is random, so there could be variations. Then it's called cyclostationary. It is a cyclic or cyclic process. The same thing happens every cycle or every beat. The heart rate could change, so you use the ECG as a trigger and say this much and that much from the next beat, and that much should be the same. Then you can average, create an ensemble of those pieces and average them, which we do in that book you saw in biomedical signal processing, to average across multiple observations of the first heart sound only, second heart sound only, over multiple cardiac cycles, using the ECG as a trigger. Or similarly, you have other applications where one signal is used as a trigger and another signal is acquired and averaged in an ensemble. So cyclostationarity helps in creating an ensemble of a signal that really is continuous, but you're breaking into parts and synchronizing them. In gated blood pool imaging, nuclear medicine images of the heart are acquired in several parts over short intervals of time. If you take a picture in nuclear medicine imaging, a radio isotope is injected and it is tagged so that it goes to a particular part of the body, such as the left ventricle, and then you take pictures. But to take a picture, it takes several seconds. The gamma camera needs to count photons over a few seconds. But over a few seconds, the heart has gone through multiple changes depending on the heart rate. So this averaging or counting of photons over a long period of time cannot be done continuously. So you take the ECG and find the QRS complex, the beginning of the beat, and then break each cycle into parts. And for each phase of the cardiac cycle, you gather the counts and make an image. But that image is not useful because you don't have enough counts. There'll be too much noise. So the next window you put in the next frame, and maybe you take 8 or 10 frames per cardiac cycle. And when the next first heart sound comes, or the QRS complex comes, you put that to the first frame, second frame, and so on. So this is called gated imaging, using the ECG as a gate. So this takes to benefit cyclostationarity. Otherwise, it's not possible to get a picture of the heart using an imaging system that requires counting of photons over several seconds. The covariance and cross-correlation are two more measures. We saw autocorrelation. In cross-correlation, the signals are different, not just the same. In terms of the expectation value, the sigma value is expectation of f minus mu f times g minus mu g. Previously, it was f minus mu square. So now you have two functions, two images, f and g, their means, and multiply with the joint PDF and integrate on both of them. So you need the joint PDF of the two processes. Covariance is normalized, sigma fg over sigma f sigma g, and then it is between plus and minus 1. High covariance indicates that the two processes have similar statistical variability or behavior. Not that they are identical, but similar variability. And they're uncorrelated if rho fg is 0. The statistical independent processes are also uncorrelated. The cross-correlation function is expectation of fxy with g x plus alpha y plus beta. So you apply a shift to one of them. So this facilitates analyzing the nature of variability and also template matching. I have a template of something I want to detect, and I expect it to be present in the image, but I don't know where it is. So I create an image of this, and then I go like this, multiplying and integrating over this space and with a shift. And when a large value is found, and I have found that object. That is used in radar in 1D signal processing to detect return signals you get from a signal that you send out, an echo, and that's template matching, which is related to cross-correlation. I mentioned earlier that we typically assume noise to be independent of the signal, but there are situations where, in imaging especially, noise is dependent upon the characteristics of the signals or the value of the signal, so you cannot treat them as uncorrelated. The noise is functionally related to or dependent upon the signal. And how you define that, for example, for some noise, I gave you one expression earlier. Here is another expression. The probability of occurrence of a certain value G naught Mn is dependent upon Fmn, the original signal, and some factor lambda. And you don't need to remember this, but the probability of occurrence of this value G is dependent on the original value F in this relationship. There's some exponential factor, but this is raised to the power of G naught Mn, G factorial, like K factorial we had earlier. So this shows that the PDF depends on the signal and some factor, the PDF of this value being observed. So Poisson noise is one case where it is signal dependent. So the expectation of G naught Mn, it turns out to be lambda expectation of Fmn. And normalization is done this way. Gmn is G naught over lambda. That facilitates some analysis. So with some normalization, you may convert signal-dependent noise to signal-independent noise, and then your further analysis is simplified a little bit. So Poisson noise may be modeled as stationary additive noise in this manner if you take sigma eta square to be expectation of Fmn over lambda. This lambda factor provides that, facilitates that assumption. Film grain noise is often encountered not only in medical applications but other applications in aerial photogrammetry and so on, where film used to be used. Nowadays, most of it is digital, but there are still some high-resolution imaging applications where film could be used. And when you scan film to high resolution using some imaging device, laser or CCD, you encounter film grain noise. The granular structure of film due to the silver halide grains contributes to this noise. The structure of the film itself, which is not uniform at the level of the resolution you'd scan. If you use poor resolution, you may not encounter that. So there is a model given by this equation. Gmn is Fmn, the original signal, plus this factor. Now this factor, kappa is some scale factor. This script f is some function of Fmn, of the original signal, which you don't know, of course, times eta 1, multiplicative noise, plus eta 2, additive noise. So this is a general model which includes both multiplicative and additive. And if you assume kappa is 0, then it's only additive. But you need to have some idea of what this function is. And yeah, I already mentioned that. One of the assumptions is to use a square root, Fmn to the power of p, with p equal to 0.5, so it's square root. That's a commonly used model. So kappa square root Fmn times eta 1, multiplicative and signal dependent. So this causes some complications. There is a model given where film grain noise may be modeled as additive noise, eta mn kappa square root, that's a function dependence, eta 1 plus eta 2. That's what is given in this model. And the mean and variance are given by this equation. Again, you don't need to remember that, but if you need to, you can refer to that. In synthetic aperture radar, speckle noise is encountered, which is again multiplicative. Gmn is Fmn times eta 1. The distribution in this case is typically not Gaussian. It could be exponential or Rayleigh or Gaussian sometimes. The multiplicative model may be converted to an additive model to facilitate further processing by modeling the variance in this manner, where you have sigma square g, the variance of the observed signal, its mean square, and this ratio sigma square eta 1. And that is the space variant signal dependent variance. Mn indicates it is space variant. So there are some transformations and manipulations of this nature which help in converting signal dependent noise into some other type of noise that facilitates further processing. So there are a few papers where this kind of a transformation has been applied. TGM is alpha square root GMN. So that is normalizing, alpha is a normalizing constant. And the noise in the transformed image is additive, has a Gaussian distribution, and so on. Okay, so I quickly went through some of that. Now, how do you apply some of these concepts to get better images, filter noise, and achieve reduction of artifacts? So let's look at some procedures and examples. The first one I mentioned is synchronize or multi-frame averaging. I take a number of pictures of the same scene, assuming no change, no motion change, no change at all in the structure, except for noise. Then average. Noise will be reduced by averaging. So this is known as multi-frame averaging or synchronize, because you have to synchronize your image acquisition with something. If there is variation, such as ECG, you can use that and synchronize acquisition to that. But if nothing is changing, then simply take multiple images. If an object can remain free from motion, internal or external, over a certain period, then you can acquire several frames of images of the object. Then you average them, known as multi-frame averaging. So as I mentioned, if there is variation, if there is a trigger that can help you in identifying the same phase of the activity, such as the ECG, doesn't have to be periodic. The ECG is not perfectly periodic, but a trigger helps in identifying where something is happening. And you take portions of the signal synchronized to that activity. So then it is synchronized averaging, and it is a kind of ensemble averaging. You're getting ensembles of images taken at a certain instant in a situation which is changing, but the same thing is happening repeatedly. So the cardiac system, whose phases of contraction are indicated by the ECG signal, facilitates such acquisition of images in nuclear medicine imaging. So the model is very simple. GIXY is FXY plus eta IXY. FXY, the original, is the same. GI is the ith acquired image. Eta I is noise in the ith image. But you may assume the noise is the same from one image to another. So the same noise is happening. So assume that the noise is independent of the signal. The original image fxy is the same. Then it follows that the variance of GI is equal to variance of the noise only, because the signal is fixed. fxy has no variance. If m frames are acquired, g bar xy is 1 over m, I going 1 to m, gi xy, just adding all the frames and dividing by m. If the mean of the noise is 0, then mean of the noise will tend to 0. The average of the noise, the 1 over m, if you want, the average will tend to 0 as m tends to infinity, or is large. Then expectation of g bar is equal to f, the original image, and you can show that the variance of sigma square of g bar is 1 over m variance of noise. So the variance of the observed image reduces with the number of images that you are acquiring and averaging. So the variance is reduced by a factor of m. The SNR is improved by a factor of square root of m, because you're using the variance here. So motion or change between the frames will lead to distortion. If I take a number of images, if somebody moves, then there is some blurring or something happens, which will cause distortion. But in the absence of that, you will get an improvement in SNR, signal to noise ratio, by a factor of square root of m. This is just a synthesized example. We created a number of test patterns like this by randomly placing various shapes with various gray levels and then adding noise. So this is the original image with noise. This is with noise, Gaussian noise added. And this is another version with Gaussian noise added, not exactly the same, but different noise samples added to the original, and results of multi-frame averaging using 2 frames. If you average these two, then noise is reduced to some extent, but if you average 4 frames or 8 frames, you get a smoother result without blurring of edges. So you can take this and zoom and look at the details later if you wish. So the more the frames you average, the better the signal to noise ratio. I'll show the nuclear medicine example later towards the end of this chapter. I'll place some examples at the end of the chapter as applications. Space domain operations using local statistics, like temporal moving window averaging of one-day signals. If you don't have an ensemble of images to do multi-frame averaging, given only one image, you average over space using a local window. So given a single noisy observation of image of some finite size, we do not have any access to an ensemble of images, and you may not even know the PDF of the image. So spatial statistics are computed over the image. But if you do that over the entire image, that doesn't help. You get one value, and that doesn't help. So we should accommodate for non-stationarity of the image too. So then you go for local statistics. A moving window filter uses windows of small size, typically squares, 3 by 3, 5 by 5, 7 by 7, but later on I'll show other types of windows. Rectangular windows as well as windows of other shapes may be considered when appropriate and when you can design something for the specific application. So all you do is say, okay, there is a position here, I'll take that window and process it and put it at that location. Next I take that position and take that window and do something and put it at that location in the output, and for every pixel. So that's fairly simple. So this is a moving window over the entire image, and at the center of the window, you position that window at some location, and you compute statistics or do some operation on the pixels within the window, and apply that result in the output image at the location of the center of the window. Note that only pixel values in the input image are used. The output is in a separate array. There are different shapes of windows that one could use and that have been recommended in some books and research papers. It depends on what kind of artifacts are caused by the windows and which kinds of artifacts are acceptable and which are not. So the common one is 3 by 3, all right? It's also called 8 connected. There are 8 neighbors to this pixel. If you don't want to take the corner, because the distance from here to the one above and to the left and right and bottom, that's 1 pixel distance, but this distance is square root of 2. So it's not the same distance. So you may say, no, I don't want the corner, I'll take only 4 connected or integer distance 1. Then you get that shape. A vertical bar, horizontal bar, a bigger square, and if you trim the corners, you may call that a circle, approximate circle, a cross, bars, again, longer bars, and some other shapes. It all depends on what kinds of patterns exist in the input image and how they are distorted by these filters. There will be distortion. And which patterns are of interest in the application to the end user, and how to prevent artifacts that will not be suitable in the application. The main filter is simply taking the average. But there are assumptions. The image component is relatively constant, that is quasi-stationary. We assume that within the window you're using, the image is stationary. If I put a small window here, okay, that is stationary. I move, I come here, but then this thing got inside my window. Now it's not stationary anymore. But I still assume it is stationary. When I average, that gets blurred. The value of this is spread over. As I move the window, this comes in, and again, not stationary. So That's where the method fails. All methods work to some extent in some applications, and they have limitations. So one must be aware of the limitations. The only variations in the neighborhood are due to noise. That is, all the pixels in that window are related to the signal at that location, and the variation among them is only due to noise. So by averaging, noise is reduced. Noise is additive, noise is independent of the image or signal, and noise has zero mean. These are the assumptions made. The 3 by 3 we saw earlier, this is the current pixel, and you take the neighbors and just average them. We saw the convolution mask also, which is this. So this procedure is convolution. It's a linear process. It's a linear shift invariant process. The same thing is done everywhere. And the point spread function, or the impulse response, is that. There is a problem at the edges, because when the image ends here and you want to put the mask here, centered at that pixel, you don't have anything outside the edge. So what do you do then? You may say, well, I don't process it. If you put 0, then output will have a border. If you put the same values, then there'll be noise there. So you may say, well, for this point, I have these neighbors. I'll use only those neighbors, 1/2 of the window, and process. So that'll give you perhaps a passable result. So you may extend the input with a border of 0 valued pixels, which is effectively what I said. Or you do not process, but that leaves noise. Replace edge pixels with an average of available neighbors, which may be a better option. The mean filter can suppress Gaussian and uniformly distributed noise effectively in relatively homogeneous areas like this, or within these characters. But when you come across, when you change from when the window overlaps background and object, then there is blurring. So the operation leads to blurring at edges of the objects in the image and loss of fine details and texture. So fine detail like this dot will be blurred out. Blurring of edges can be minimized by not applying the mean filter if the difference between the pixel and the mean of the neighbors is greater than a threshold. So when you come here, when the window is sitting here, you say, oh, this pixel and its average of the neighbors, the difference is large, so I will not process it. We'll leave it like that. Then it becomes nonlinear. You put conditions, then the filter is no longer linear. The median filter may do better. The median is a sample that splits the value of the population you have in half. So you have a bunch of pixel values from a neighborhood, 3 by 3, 5 by 5, whatever, and you take the value in the middle of that distribution so that there are half the number of pixels on one side and half on the other side. That's the median. This is typically done using a rank ordering process. It's not necessary to rank order all of them, but you can do that. You use an odd number of pixels in the neighborhood, like 3 by 3, 5 by 5, so that you can find the pixel in the middle of the distribution. So the value at the middle of that list is, after rank ordering, the middle value is selected. It's a nonlinear filter, but it can reduce noise without causing blurring. But there are some other problems which I'll illustrate. So it provides for better noise removal than the mean without blurring, especially when the noise has a long-tailed PDF, resulting in outliers or salt and pepper noise. If you average salt and pepper noise using a mean filter, you get blotches at every location of the salt and pepper noise. But the median filter could result in clipping of corners and some distortion of shape, especially if you have strong edges, then there will be distortion of shapes. And median filtering with large neighborhoods could result in the complete elimination of very small objects, such as a little dot. That'll go away when you apply a median filter. Non-square neighborhoods, like the other shapes I showed, they are used typically in median filtering to avoid distortion of shape. So here's a simple example with a 1D signal, just a block here, a rectangle, and I added some spike noise, salt and pepper noise to that. And if we apply the mean, you get this, which is not very good. The mean filter was applied with n equal to 3 samples. If you apply the median, you get the original back. But this is a synthesized example, a made-up example, but it shows how median is better than mean in such cases. But here we have uniformly distributed noise. The original, I added this spike, a small rectangle and a big rectangle. Let me not call it a spike, with uniformly distributed noise added here. The mean filter and the median. The median filter has suppressed this small pulse. Was that a pulse of interest or was that noise? I don't know. I cannot tell. So if you believe that is a signal of interest, then this is not good. But look at the edge here. The mean filter has blurred the edge. The median filter maintains the edge. This is blurred, this is straight and sharp. So in most cases, the median filter does a good job. But the question is, what kind of a neighborhood you want to use and how many samples to compute the median. The root mean square error or mean squared error, MSE, they are used to compare results of various image processing systems. If you have a test image, you can take the distance between the test image and the various filtered images, or the noisy images and the filter images. You need some reference. An image with a higher RMS error may present visual better quality than another with a lower RMS error. Several studies have shown that RMS and mean squared errors don't really correlate well with human perception. The noise level could be high, but we may still be able to perceive the details and the sharpness of the objects. But if you blur the edges, then you may not like it, even if the RMS is low. So these measures of error and quality that I showed earlier, they may not always agree with human perception. So that's why there are some measures related to perception. And you have to check with some comparative analysis as to whether the measure that you propose agrees with visual perception as computed in some numerical manner from a number of observers, not just one person. So visual inspection and analysis of the results by qualified users or experts in the domain of application is important. A radiologist is the one who will decide if my image processing method is suitable for mammograms. Not a cardiologist, not me, not somebody else. So here are some images. The test image with noise and 3x3 mean filter, 3x3 median filter, 5x5 mean, 5x5 median. So these two are median filters. These are mean filters. Clearly you can see blurring of edges, especially when the window is large. Compared to that, even compared to the noisy image, this is very blurry. Noise has been reduced. Yes, this is smooth. But the edges are blurred. Look at the median output. The edges are sharp. There is a little bit of blurring here. But the corners have been clipped. So there is shape distortion. This is not a rectangle anymore. And those small little triangles there, they're all gone. When you take the median over a big window, these are smaller than half of 5x5. So they're gone. So if you apply the median filter with a big window, calcifications may disappear from the mammogram. So we need to know the limitations of these. So that's why I have used these synthesized images. They were not designed specifically, but these artifacts have happened here anyway, and you can clearly see that. You may not be able to perceive that in a real image. This is with Poisson noise. The median filter works a little better. The RMS values are given here. I won't read that. They're just numbers. So we have shown with different types of noise, with speckle noise and so on. But the best illustration perhaps is with the salt and pepper noise, where mean filter fails with a small window. Larger window, the noise is reduced, but very blurry result. The median has done better, but again, the small objects are gone. But this heavy noise here, with a density of 0.1, salt and pepper, most of that has been removed. So you need to know something about the image as to what is the smallest object of interest, so that you can design an appropriate filter and window. These are histograms of the test images with different types of noise. This is the original, very separated values of different objects. So a bunch of delta function kind of impulses in the histogram. When you add Gaussian noise, we get this. It's all positive. The pixel values are all positive, so you don't have the other side of the Gaussian. Poisson noise and speckle noise. It's a little difficult looking at the histograms to judge what kind of noise it is. I thought we could perhaps see some difference, but it's not so, except in the Gaussian case. So here are some real images. These are test images from the time image processing started. Way back in the 70s and 80s, there were not many databases of public images, or not many people had digital images, or the facility to scan printed images. At IISc, I joined the Indian Institute of Science in 1976. I took a course from Professor G. Krishna on digital image processing, and we had a lab where there was a scanner. You will laugh at this, but it was very interesting and innovative, using what is available to scan prints of paper or photographic prints. The print would be mounted on the drum of a lathe machine, you know, the wood turning or machine turning lathe. It was mounted there, and there was a laser source, and the lathe was run. And as the drum rotates, the one row of the image or column, whichever way you see, is scanned. The laser is fixed, and then it is translated. The stage is translated, and you scan. So as the drum goes, you get sort of a helical scan, but the picture is smaller than the circumference of the drum. Yeah, so you get these scan lines. And if you wanted to scan a transparency, there was a hole cut in that drum, and you would mount that, and you had to have a laser beam somehow else. You need to get the beam going through the film. But mostly we were doing prints at that time. So that was done in 1976 and 77. So these images, Pepper and Lena and a few others, were created in which university? There's a reference somewhere. And a database was created. So many research papers use these images. These are also in color. But nowadays, people are getting tired of this, so we need to have other examples. I'm replacing them with other images. And we have other real images too. But there is a little bit of history to these images. So that's the original and Gaussian noise. You can see the noise there. I hope you can see from the back too. The effect of noise, mean 3x3, 5x5, median, and the median is okay. Not here. The mean is not bad. There is a little bit of blurring at the edges. It's not so obvious with the real image as with the test image. So again, different types of noise. I'll skip to the salt and pepper. This is where the median works really well. The mean fails and the median works. The others, it's a little difficult to see. This is Poisson noise, mean, median. Mean may be better here. 11.12. 3x3 mean, RMS is 11.22. Median is 8.56, but to me this looks better. It depends on your perception. The median filter actually is an order statistic filter. Order statistic filters are a different category of filtering signals and 1D or multiple dimensional signals, where you take a population of your values of the signal or image using a certain neighborhood or window, and typically you take an odd number and you rank order them minimum to maximum, and the ith entry in the list is the output of the ith order statistic filter. That's all. The min filter is the minimum, that's the first one in the list. Max is the last one when they are rank ordered. So the min will help in removing isolated bright spots, the salt noise that will be at the end of the list. And the max will remove isolated dark spots or pepper noise, which is at the opposite end. You select if you select the max. The median is in the middle. If you combine the min and max, you can remove both salt and pepper noise. The median is the entry in the middle, as you saw already. And then there is the alpha trim mean filter, which gives you flexibility, where the mean of a reduced list, you don't average all of the values in that list. Some could be corrupted by noise substantially, and they'll be at the ends of this list. So you want to take only the values in the middle of that list. So you throw away a few values at the beginning and end of that list, very small values and very large values. And the median is giving an approximation of the center of that distribution. And now you say, instead of taking one value only, I'll take a few values in the middle and average them. So it's a combination of the median and the mean filter, but not indiscriminate mean, not averaging everything. So it says you reject the first alpha and the last alpha being a percentage between 0 and 50%. Outliers are rejected. If alpha is close to 0.5, almost the whole list is rejected except the middle one, which is the median. So you tend towards the median. The output is close to or equal to that of the median. So if you use alpha equal to 0.4, 0.3, depending upon how many pixels you have in that population, the window that you have chosen, the mean of the trimmed list provides a compromise between the mean and the median. So that's one of the order statistic filters that is flexible. Now there is another filter called L filter. You have the ordered list and you give weights to all of them. The weights should add to 1 so that there is some kind of averaging. But you could apply different weights. You could do even a sort of convolution if you want. So it's a weighted combination of all of the elements, and using appropriate weights you can get all of the filters that we have seen so far in this section. So selecting a window of pixels and rank ordering them and performing these operations will help in reducing different types of noise. Okay? Any questions or comments on this part?
These days we don't see, researchers or students, to say, they don't see the images, but they read the CSV files.
You're okay with 30 minutes more, or are you tired? Tired, and you don't want to say that. 15 minutes. Okay, let's go for 15 minutes. I'll stop at 15. As I said, the initial plan was for me to give 40 hours of lectures, and I have signed that document, so I'll talk for 40 hours. Otherwise, Gian will not invite me again. Oh, it is being recorded, so I should be careful.
That's okay, sir.
No, I didn't say anything bad. So frequency domain filters now. All of the filters we saw so far were in the space domain using pixel values. But we talked about low pass, high pass, and all that. And typically these filters, low pass, high pass, are designed and applied in the frequency domain where low and high mean frequency. So let's see some frequency domain filters. So most images of natural entities and natural scenery vary slowly and smoothly across space. And they don't have sharp edges. There could be some, but this is not natural. This is a machine-made or man-made object. But if you go outside and take a picture, yes, there are trees with some edges, but overall, there is some smoothness. Most of these images have a large portion of the energy concentrated around the DC, UV equal to 0, 0. Uncorrelated random noise fields have uniform, flat, or white noise. Their spectra will be constant. So the SNR of a noisy natural image is not constant across the frequency range. The SNR could be high in the DC and low frequency area and could be poor in the high frequency area. Noise is constant, signal is high there and it becomes low. So signal becomes low in the higher frequency zone, noise remains the same. Note that noise is existing right across the entire spectrum. So the low frequency region, middle frequency also have noise. So when you do low pass filtering and remove high frequency, the noise in the low and middle range will be there in the output. They are not removed. So to achieve some smoothing and removal of high frequency noise, you can apply a low pass filter, remove or suppress high frequency components. But removing high frequency components along with noise, you lose some desired image components which are related to edges and fine detail, fine texture. So there is always some loss. You reduce noise, but you also lose sharpness and fine details. Noise components in the low frequency passband will continue to exist in the image. So what is the procedure? You compute the 2D Fourier transform, FKL, design an appropriate 2D filter transfer function, HKL. And typically you would want this to be symmetric. Obtain, and most of the cases isotropic too. Obtain the filter image, GKL is HKL times SKL. You multiply point by point in the frequency domain. And you have to take care of centering. Is the spectrum of the image centered with DC in the middle? If you did that, then the filter function HKL must also have its DC response in the middle. That's how you normally specify filter functions. But the FFT of the image will not give you the centered spectrum. So you have to center it or shift it. So usually HKL is real, affecting only the magnitude of the input spectrum. You don't change the phase. If you change the phase, the output could be affected in manners that are hard to predict and distorted. With real valued images, HKL should maintain conjugate symmetry. So the filter function has to be symmetric. The input image is real, its Fourier transform has conjugate symmetry. So HKL must be conjugate symmetric, but it is real, so it will be symmetric. But typically one uses isotropic filters, so radially it is the same. FKL may have to be centered or folded depending upon how you have created HKL in your software. Compute the inverse Fourier transform. If FKL was folded, then it must be unfolded and then do the inverse transformation. If it was zero padded, then trim the result and get only that portion that has the image. So that's the FFT-based processing or DFT-based processing. So removing high-frequency noise, you use low-pass filters. The assumption typically made is noise is additive, Fourier components of the original image past a certain frequency cutoff are negligible. So you say, I'm going to cut there. But there will be some loss of some frequency components of the signal. The so-called ideal low-pass filter has a sharp cutoff. It's a rectangular gate function. Your low frequency components up to some frequency and then gain is 0. Gain is 1 and then 0. So that sharp transition causes problems. When you have such a sharp transition and one of the signals is band limited, its Fourier transform cannot be limited. If you have a band limited function, it is not time limited or space limited. If it is space limited, it is not band limited in the frequency domain. Like the rectangle function is space limited, but its Fourier transform sinc function goes forever. Right? And if it is an impulse in the frequency domain, it is band limited, but its inverse Fourier transform is a constant forever, all space. The ideal low-pass filter is defined to have gain 1 up to some frequency d0, where duv is the distance from the origin, or square root of u square plus v square, uv being the horizontal and vertical frequency coordinates in the Fourier space. So d0 is the cutoff frequency. But the ideal filter creates problems. The name ideal means there is a sharp transition, pass band, stop band. But that, it might work well in time domain applications, and it is called ideal filter there too. But in image processing rather, it creates serious problems. So it is not ideal or suitable here. But anyway, the filter function looks like this, a circle. That is, DC is here up to certain frequency, you pass, and after that the gain is 0. That's a Butterworth low-pass filter. We will get to that later. If you take a section, the ideal filter is that. Sorry, it's a little difficult to see that in this plot, but there is a line there. That's the ideal filter up to 0.2, and after that the gain is 0. The Butterworth filter has a smooth transition, monotonically decreasing function. And this is 0.5 normalized frequency, half the sampling rate. 0 and minus 0.5. A glaring artifact, because of the ideal filter, is echoes of edges. Because the inverse Fourier transform of a rectangle is a sinc function. Sinc function has side lobes, positive and negative. Multiplication in the frequency domain with the rectangle causes convolution in the image domain with the sinc function. A sinc function, when you convolve, it gives you positive and negative sort of reverberations or echoes. And one edge will cause multiple artifacts, positive and negative edges. So the inverse Fourier transform, if it is a sorry, we are not using rectangle, we are using a circle, so it is a Bessel function. A section is a rectangle. But the 2D function is a circle, so it is a Bessel function, similar positive, negative side lobes. So this is known as the ringing artifact. The ripples or lobes of the Bessel function lead to echoes of strong edges and objects and causes this ringing artifact. So you see these patches. The edge here appears, and that edge is echoing here, and it goes all over. And they all interact and mess up the image. So this is the original with noise and ideal filter. That is the Butterworth. We'll come to that later. So can you see that? The patches here, and see the triangle here, and bright edge, and a dark line there, which is the ringing of that. And there will be a similar one here, a negative one coming here, which will reduce the intensity inside. Some of that may not be clearly visible. If you zoom it and look at this image on your screen, you may see better. So this is the spectrum of the shapes test image. This is with noise added. It's a little hard to see the difference. The Butterworth low-pass filter is defined in this manner. Gonzalez and Woods have this definition. In 1D, it is defined in a similar manner, but not exactly the same. What you want in a good filter is a maximally flat response in the pass band and suppression in the stop band, and a transition that is as fast as possible between the pass and stop bands, but you want a monotonically decreasing function. Sharp changes in such a function will cause repercussions in the other domain, in the image domain, that are not desirable. So you want this function to be smooth, and the Butterworth function is one that has a maximally flat response in the pass band, and it is monotonically decreasing. It is defined as this 1 over 1 plus a scale factor, the frequency, which is defined as DUV, distance from 0, square root of u square plus v square, divided by d naught, that's the cutoff frequency, to the power of 2n, where n is the order of the filter. If you refer to my 1D signal processing book that was being passed around, there is more information about this in the 1D case and how to derive it. So for a Butterworth filter of order n, the first 2n minus 1 derivatives of the squared magnitude response are 0 at omega at equal to, or frequency equal to 0. We don't use omega, but that's in 1D. So that is what is meant by maximally flat. Not only the value, but its derivative and so on. How many orders of derivative depends on n. So the larger the n, the flatter the response in the pass band, and faster the transition from the pass band to the stop band. So those are the properties of this filter. And it is monotonic in the pass band and stop band, and monotonic in the transition too. So DUV is square root of u square plus v square. D naught is half power cutoff frequency. The gain is equal to 1 over root 2 at the cutoff frequency. Or the power is 1 over 2. So here is an example. This image of a clock in our lab. We took it using an old video camera, digitized it, a lot of noise, and the spectrum of the image. And this hand, you see the directional component there. There are horizontal vertical edges giving that. I also zero padded, so which has caused some additional artifacts there. So this is with ideal filtering. You have these ringing artifacts, and this is with the Butterworth filter that does not have any ringing artifacts. There is smoothing. The filtered images are smooth, which is what you want. How much smoothing? You design an appropriate filter with appropriate cutoff and order of the Butterworth filter. This is already blurry, and there is more filtering, but the ideal filter introduces these artifacts. The Butterworth is free of that artifact. And go back, and here also, the Butterworth filter is free of the ringing artifact. Noise has been suppressed to some extent. Not all the noise is removed, because noise in the low frequency and intermediate frequency will stay. So there is some noise here. It's not like that. And sometimes it may introduce some false texture. You may think it is, or you will perceive some texture, but that is false. That is filtered noise. So that's the difference between the two filters. There could be some periodic artifacts, sometimes with grid lines, as I mentioned. And if you have a picture that is drawn on some sort of a graph paper, then there are these vertical and horizontal lines. Periodic components give rise to impulse-like periodic concentrations of energy in the Fourier spectra. Periodicity means there is a pattern and it is repeated, and repetition is convolution with a delta function. You repeat the same thing. So when you have some pattern that is repeating, it implies that there is a basic pattern or motif, and that has been convolved with a delta function that has a number of delta functions. Periodic or not, there are repetitions. And at every delta function, this pattern is copied. And if the delta function train is periodic, then you got a periodic pattern. So if you have grid lines that are periodic, then there will be impulses in the Fourier domain at the inverse of that spacing, which is the frequency. So this facilitates removal of periodic artifacts if you know what the period is, or you examine the spectrum of the distorted image, and if you see points of high intensity, that indicates periodic artifact, and that should be visible in the image too. So you remove these artifacts. How do you remove is a question. I was discussing with one of you earlier about this, and if you just use a notch filter and set those values to 0, you will have artifacts, because the original spectrum didn't have 0 there. You can assume the spectrum is continuous, and at the location of these spikes or impulses, you average and set it to some values in between that will make the spectrum smooth in that range. Or apply some sort of filter that does not cause large discontinuities in the spectrum. So removing the artifactual components lead to the loss of frequency components of the desired image. They were added, but the image has some energy there. You need to preserve that and remove only the artifact. That is a bit of a challenge. So here is an image of a part of an image of a mammographic phantom with calcifications. There are various phantoms for various parts of the body and different imaging modalities. A phantom is a test object that is created by various companies. They manufacture and sell them. You test your imaging facility with that, imaging system with that. And there could be some grids there, and you want to make sure that the high frequency grids will still be visible with good resolution in the image that you acquire. And calcifications such as these fine spots should be clearly visible. You measure the contrast and so on. So for each type, each body system or part and each imaging system, there are various phantoms. I asked Dr. Hahn, my colleague in nuclear medicine, to take a picture of this phantom with and without the grid moving properly. The grid has to move during the X-ray image acquisition procedure to get a smooth image, to reduce scattered photons and scattered noise due to scattered photons. But if it doesn't move, you get these lines. Those are the grid lines. And these bright spots are the calcification simulating material in the phantom. This is the spectrum of the image. The lines are horizontal with some spacing. So horizontally, each line is a constant. So it doesn't have any component in the horizontal frequency, but in the vertical frequency, there is that variation, and you get these spikes. Periodic, there is DC, of course, and then that, and so on. So when you see that, we say, oh, there is some artifact, clearly. There is also smearing this way, which could be due to aliasing or could be due to the fact that I'm using a finite window to compute the Fourier transform. Otherwise, you should only see these spikes. So to remove that, I thought, well, I'll just punch out those spikes and set to 0. That's not a good filter, but these are the regions I blocked out. A very bad filter. But I want to show you the artifacts also that are caused by the filter. So all these blacked out regions are where my filter was set to 0. And this is the output I got, which is, the grid lines are not there, but you see the artifacts because there is discontinuity here. So a better filter would have been to, if you take a section here, so there is some, let's say there is some spectrum, and suddenly there is this spike, and then it goes on, and then there is a spike. I set it to 0 and totally eliminated that, and then the spectrum goes like that and goes to 0 and comes up again and then goes to 0. And that discontinuity gives rise to artifacts in the image domain after inverse transformation. What I should have done would be something like this. Keep all of that, and where there is a spike, apply some interpolation, and then keep the rest there. And then where there's a spike, apply interpolation, fill the gap, and make it continuous, make it smooth. Assume that the spectrum is continuous, which may or may not be true, but there should be some continuity. Are those the real values? I don't know. I don't know what was there before the noise. In any case, this is what I got, which is not the best result, but I want to show what works and what doesn't work also. If you want to design a better filter, you could try something like that, to interpolate and fill the gaps. This is the original image if the grid has worked properly. Now, you wouldn't take such with and without grid movement with patience, of course. You can't do that twice. So with the phantom, we could do such a thing. So this is how it should have been, and its spectrum. The filtered one is not like that. All right, we will stop here. It's a little past 5:15. Matrix representation of image processing involves some more mathematics. Of course, there's a lot of mathematics. And we will see some optimization procedures based on matrix representation. We will see that tomorrow. Are there any questions or any comments? Am I clear, and are you following the presentation and discussions? I had a couple of you come and talk about other things, but is this clear? Please do go through the notes, because I've skipped some parts, and in order to really get all the details, you should take each equation and work through. Not today, not tomorrow. It's a nice place. Go to the beach and walk around. But later on, please go through that, and that procedure will help when you design your own research algorithms. That experience helps. And you could also create phantoms and test pictures and write your programs and work with them before applying your methods to real-life images, because these phantom images will show you what is good and what is bad, what is working and what is not working, what are the artifacts that are removed and what are you introducing by your technique of whatever filtering you're doing. Whereas when you apply it to a real image that is so complex, it will be hard to see such details. Any comments, questions? All right, thank you. So tomorrow we meet at 9:30 here?
Yes.
Not 9:15.
So we have come to the end of the day one, and so tomorrow again 9:30 we'll meet here. We'll thank Professor Rangarajan for the day one. So I know that the
Thank you.
will be very tight and it will be more dense. Probably that's the difference between usual Indian context and the foreign context, how it will deal with that. So thank you very much. We'll stop here for the day.
Actually, we got this through our Indian professors at Indian Institute of Science, right? So, no, I'm trained here, so yeah. Okay, thank you. See you tomorrow.
We'll stop at Yes, meeting with